Hi guys, today we're going to talk about Le principle, which is one of the more famous things in chemistry for those of the people who know about it. But before we get into the specifics of it, just know that Le principle is kind of the petulant two-year-old's principle. If you've ever had any experience with two-year-olds, you know that their favorite word is no. Whatever you ask a two-year-old to do, not only are they not going to do it, but they're going to do the opposite of it. So if you say to a two-year-old, come here, the first thing they do is run away. If you say to a two-year-old, go away, the first thing they're going to do is follow you around no matter what it is that you do. You try to give something to a two-year-old, they don't want it. You try to take something from a two-year-old, good luck. They will fight you to keep it tooth and nail. So basically the idea of Le Chatelier's principle is whatever you try to do to a system that's at equilibrium, you got to treat that equilibrium like it was a two-year-old. It was already perfectly happy the way it was. If you go and mess with an equilibrium, it's going to do everything it can to undo what it is that you just did in order to re-achieve the equilibrium that it had established. So let's take a look at this equation. Now this is a little bit goofy because normally we ignore water because water is our solvent. But in this particular case, it's a little weird because water is actually a reactant and we've dissolved these things in alcohol. It's one of the very few times this will ever come up. I don't think it ever will, but this is such a good example that forgive the weirdness. But these substances are dissolved in alcohol rather than water in this particular case, and it matters. So just know that there is an equilibrium established between these two substances. This guy here, the cobalt with a +2 charge and 4 chlorines to give it an overall -2 charge, that substance is blue, but this substance over here is a pink substance. So right now it is obvious from this picture that we have way more blue of substance than we have of the pink substance. So that's just for right now. Right now I have more of this and I have less of this over here. All right. But watch what happens. What I'm going to do here is I'm going to take this substance and I am going to add water to it. Now, normally water is not involved, but because water is a reactant and not the solvent in this particular case, this guy is involved. Let me prove it to you by showing the Kc value for this. Here's the Kc. It's going to be that pink substance that we had here, raised to the first power. It's a +2, just because of the charge that's there. And then it's going to be 4 of the chlorines that are here, these guys here. So it's going to be the chloride negative to the 4th power, like so. And then we're going to divide that by the stuff that's over here on the reactant side, which is my blue substance, which is that guy there, and then my 6 waters, which is this guy here, 6 H2Os, which is that guy there. So it's just products over reactants raised to their powers like normal, except that water is a reactant and not the solvent. So right now I've got more blue than I've got of the pink. But what did I just do? I added a bunch of water to this. Well, if I add a bunch of water to this, now it's no longer at equilibrium. From a mathematical perspective, what I have just done is I have made the amount of water go up. And if I make the amount of water go up, now all of a sudden, what has that done to my K value? Well, first of all, it's no longer K, it's Q, because it's no longer at equilibrium. And if I am now dividing by a bigger number, that's going to make Q too small. And what did we learn about in the last section? If Q is too small, if Q is less than K, then it's going to go to the right-hand side because it's going to try to make these numbers here get bigger. And it's going to try to undo the thing that you just did, which is to make those numbers smaller. So what it's going to do is it's going to take this and it's going to send it from the blue side over to the pink side. It's going to increase the amount of these substances, and it's going to decrease the amount of these substances, which is going to make the amount of pink go up, and it's going to make the amount of blue go down. So it's not surprising, once I added the water to this, it turned pink. All right. Well, now, eventually, it will reestablish equilibrium with different numbers. And now I've got more pink than I've got of the blue, which is fine. So more there, less there, but I have reestablished equilibrium because the color isn't changing anymore. But now, guess what I'm going to do? I'm going to go mess with it again. What I'm going to do this time is I'm going to add some hydrochloric acid, which is going to make the amount of chlorine in the system go up. So check it out. So now what I'm going to do is I'm going to take the amount of chlorine, go up. Now, look what happens from this. This number now is too big. And if that number now is too big, I am no longer at K, I'm at Q, because now this number is too big. So what happens if that number is too big? It's going to try to make this number smaller and these numbers bigger because my Q is too big. So remember, when Q is greater than KSP, it's going to shift back to the left-hand side. So by raising the amount of chlorine, I'm going to shift it back to the left-hand side, which is going to increase the amount of blue that I have, decrease the amount of pink that I have. And so not surprisingly, I have now sent it back to the blue side. And so consequently, I have more blue than I have pink that is there. So the short of this is the following. If you add a species to a system that's already at equilibrium, it's going to force that equilibrium to shift to the opposite side of the added species. So add equals opposite. If you add something, it will go to the opposite side of wherever it is that you added the thing. So let's go back up here. In our first one, I added in water, and what did it do? It shifted to the opposite side. It went to the right because the water was on the left. So because I added water and water was on the left, it went to the right. It went to the opposite side of the thing that I added. Over here, in our second example, what I did was I added in chlorine. And chloride was over here on the right-hand side. And because it was on the right-hand side and I added it, it shifted the reaction over to the left, to the opposite side. So adding a species causes a shift to the opposite side. So that's rule number one. Add equals opposite. Well, think about a 2-year-old. If you add something, it goes to the opposite side. If you try to take something from a 2-year-old, it's going to try to get it back. So check this out. Now, this is a little goofy because you have to know this. You have to know that the silver ion will cause the chloride ion to precipitate out as solid silver. So what I'm going to do is I'm going to take this blue substance that's here, and I am going to add in silver to this reaction. And you might say to yourself, silver is not involved in this equation, so it will have no effect. But by adding in silver ions, I am actually reacting away the chloride ions to turn it into silver chloride. So by adding in silver, what I'm effectively doing is I am making the amount of chloride go down. So what am I doing? I'm taking something from that 2-year-old. So if I take chlorine from it, what's that 2-year-old going to do? It's going to try to get that chlorine back. So it's going to go to the side that has the chlorine on it in order to get that chlorine back. So it's going to shift to the same side over here. So our second rule here is if you subtract or if you take, it will go to the same side. So those are your two basic rules for Le Chatelier's principle. If you add, it'll go to the opposite. If you subtract, it'll go to the same side. So quick little thing here. If I have A plus B goes to C plus D, and I tell you I'm going to add in A. So if I add in A, that's going to make A go up, and that's going to shift the reaction over to the product side because when you add, it goes to the opposite side. Instead of adding A, I'm going to add in C. I'm going to make C go up. Well, if I add C, and C is on the right-hand side, then that's going to shift it over here to the left-hand side. It's going to go over to the reactants side over here. Well, what happens if I take away or I subtract C? Well, if I subtract C from it, it's going to say, hey, where'd all my C go? And it's going to try to go over here, and it's going to go to the same side that it's on. But instead of taking away C, let's say I take away B. It's going to say, hey, where'd all my B go? And so it's going to shift over to the left-hand side in an effort to try to make more B out of the situation. So your basic rules are very simple for Le Chatelier's principle. If you add, it goes to the opposite side. And if you subtract, it'll go to the same side. So all you have to do is look at the problem and decide, are you adding or subtracting? And if you're adding, it shifts to the opposite side. If it's subtracting, it shifts to the same side. Now, having said that, there are a few more particular bits about this, fine points that I'd like to discuss here. The next one is temperature. So remember that there are two different types of reactions, endo and exothermic. And if you are an endothermic situation, then your delta H is positive. And if you are an exothermic situation, then your delta H is negative. And if it's an endothermic situation, then the heat that is involved, remember, shows up on the left-hand side. So if they tell you that delta H is positive, or if they tell you that it's an endothermic reaction, you can put heat on the left-hand side of the equation. If they tell you that it is an exothermic situation, that your delta H is negative, then the heat is going to be over here on the right-hand side of the equation. So if I were to look at this one here in blue here, let me show you this. So if I were to look at the blue situation right now, okay, let's ignore him for right now. And I were to say, I'm going to add in heat. Well, because heat is on the left-hand side of the equation, because it is an endothermic positive situation, if I were to heat this system up, then it would shift over to the right-hand side. If I were to cool this system down and remove heat from it, then it would go to the left-hand side because that's where the heat is in the equation. So heat is treated just like any other reactant or product, except that you have to make sure that you know what side that you put it on. If it's endothermic positive here, heat is on the left. If you add, it'll go to the right. If you subtract, it will go to the left-hand side over here, all right? Now, what would happen if instead of it being a endothermic reaction, it is an exothermic reaction here? Well, let's take a look at that. If it is an exothermic reaction, then heat is on the right-hand side over here because it's negative, and if it's being produced from the system into the surroundings. So if this is my system and I raise the temperature, then it will actually send it to the left-hand side because heat is on the right, and increasing or adding makes it go to the opposite side over there. If instead of adding, I subtract and make an exothermic reaction colder, then it will shift that equilibrium over to the right-hand side, because when you subtract, it goes to the same side, and since heat is on the right-hand side, it will shift over to the same side that the heat is on by subtracting it. So what you need to make sure that you know is that endothermic positive reactions, the heat goes on the left, so it's heat plus reactants goes to products. And if it is an exothermic reaction, then reactants go to the products plus heat over here, okay? We've talked about that before. So we can actually determine whether or not this is an endothermic or an exothermic reaction, because if it is an endothermic reaction, then the heat's on the left, and if we heat it up, it should turn blue to pink. But if it's an exothermic reaction and heat is on the right, then by heating it up, it should turn pink to blue. So if I take one pink and one blue and heat them, so this picture here shows the hot, so this is the hot water, they both turned blue. So heating this guy up turned it blue. So if that's the case, then it must be an exothermic reaction, because raising the heat sent it to the opposite side, which is where the blue was. So this is not true that we have determined experimentally. So this must be an exothermic reaction, because when we heated it, the pink turned to blue and the blue stayed blue. In fact, even got bluer there. All right, a couple things to remember: that solids and liquids typically don't have an effect on the position of the equilibrium. So if we examine this equilibrium system here, you'll notice that the solid and the liquid are not involved in the Kc for this equation. So if I were to add calcium carbonate to this system, what effect would the calcium carbonate have on either of these values? And the answer is none. And so because it is a solid involved here, it has no bearing on the K equation, and so it has no effect that is there. So typically speaking, solids and liquids don't change the positions of the equilibrium because they do not affect the K values. Nor does a catalyst change the position of an equilibrium. All a catalyst does is make it easier for the reaction to go, but it's making it easier for the forward reaction to go and easier for the reverse reaction to go. So consequently, there is no effect from catalysts. So changing catalysts or doing anything like that has no effect on the position of the equilibrium either. So solids and liquids have no effect. Catalysts have no effect. They might also throw this at you. They might also say, we're going to give you an inert gas. So what would happen if I pumped in a bunch of neon to this system? If I pumped in a bunch of neon to this system, that doesn't affect the pressure of this, or this because of Dalton's law of partial pressures. And so consequently, pumping in an inert gas has no effect. So a non-participating gas typically does not change the position of the equilibrium. So there are three things that they might ask you that are all very easy. If you put in a non-participating gas, it typically doesn't do anything. If you put in a catalyst, it typically doesn't do anything. And if you put in a solid or a liquid that is not involved in it, it does not do anything. Now there is one change actually that does affect it, and that's the change for the volume. It potentially does have an effect on the position of the equilibrium. Why would that be? Well, let's say that we take this guy here, which is a gas, and a gas, right? And we take the volume and we cut the volume in half. Well, that means that the pressure is actually going to double according to Boyle's law. So if you cut the volume in half, the pressure is going to double. So what just happened is that the pressure here went up, the pressure here went up, and the pressure here went up. Well, wait a minute. All of the pressures went up. Yes. So it's all supposed to go to the opposite side. Yes. This is supposed to go to the opposite because it's on the left, and these guys are supposed to go to the opposite because they're on the right. Who wins? Well, just think about it from a numerical standpoint. You've got one gas over on the left-hand side that is trying to send it to the right, but you've got two gases over on the right-hand side that are trying to send it to the left. So who's going to win? Well, it's pretty obvious that the two gases on the right are going to win over the one gas on the left because there are multiple of them. So if you go and you change the volume of the system, you are going to have an appropriate response of the system based upon the position and number of the gases that are there. So if you take the volume and make the volume go down so that the pressure goes up, what you're doing is you're making the pressure go up, and so the system is going to try to relieve that pressure, so it will go to the side with fewer gases on it. So if I take this volume and I make this volume go down, it's going to go to the left-hand side because there's only one gas over here and there's two gases over on the right-hand side. So by making the volume go down, it's going to go to the side that has fewer gases. Similarly, if you make the volume go up, that's going to make the pressure go down. Well, if this pressure goes down and this pressure goes down and this pressure goes down, what's it going to do? Well, it's going to try to make all that pressure back. So it's going to try to make more gas here, and it's going to try to make more gas here, and it's going to try to make more gas here. Well, who's going to win? The two are going to win over the one again. So similarly speaking, if you increase the volume, which decreases the pressure, it's going to go to the side with more gases on it. And what if they're the same? If they're the same, then nothing happens. So here is the summary of that. If you decrease the volume, the reaction will shift to the side that has fewer moles of gas. If you increase the volume, the reaction will shift to the side that has more moles of gas. And if the moles of gas are the same, there is no effect either way. And that was the effect that I was mentioning before when you were talking about Kc versus Kp, and we skipped all those pages of lecture because they don't expect you to do it anymore. If you have the same moles of gas on both sides, then nothing is going to change. All right, so this guy here says, which way will the following reaction shift if the volume of the container is reduced? All right, so the volume here goes down. Well, if the volume goes down, you're going to increase the pressure, and so the system is going to say, hey, I don't want all this pressure. I can't handle the pressure. So it's going to go to the side that has the fewer moles of gas. I've got 1, 2, 3, 4 gas on the left. I've got 2 gas on the right. So it's going to shift to the right because there's fewer gas there. This guy here says, which way will the following reaction shift if the volume of the container is increased? So in this one, the volume is going up. Well, if I make the volume go up, that means the pressure is going to go down. It's going to say, hey, where'd all my pressure go? So it's going to try to get pressure back. Please note that this is a solid, so it doesn't count. It's a solid, so it doesn't count. So I've got 1 gas here, and I've got no gases over here. How does this guy get that pressure back? This one's going to go to the left because that's where the gas is. This guy here, I've got 2 gases over here on the left. I've got 2 gases over here on the right, 2 gases, and 1 is 2 gases here. So on this guy, I can change the volume up and down all I want, and it's not going to do any good because there is no preference to the left or to the right because they both have the same number of gases. So, LeChat. The summary of it is that a change in any factor that affects an equilibrium system will cause that system to react in such a way as to reduce or counteract that change. Whatever you do to an equilibrium system, it's going to try to undo. If you add, it'll try to subtract. If you subtract, it'll try to add. If you give it pressure, it'll try to make that pressure go away. If you take pressure away, it'll try to get that pressure back. If you give it heat, it'll try to get rid of that heat. If you take heat from it, it'll try to get that heat back. It's a 2-year-old. Whatever you do, it's going to try